Hello everyone, in today's video we're going to talk about the maximum principle for the heat equation. The maximum principle possesses various formulations. We're going to prove some results in order to show the final theorem. Let omega be an open state of R. The theorem 9.27 is the maximum principle for the Dirichlet problem. Let F be in L2 omega and U in H1 omega intersect C omega bar such that we get the equality 70 for all phi in H1 0 omega. Then the minimum between the infimum of U on gamma and the infimum of F on omega is smaller or equal to U, which is also smaller or equal to the maximum between the supremum of U on gamma and the supremum of F on omega for x in omega. A remark on theorem 9.27: for the hypothesis U in H1 intersects omega bar, if omega is C1, we can suppose the hypothesis U belongs to C omega bar. Using the truss theory, which allows us to give a meaning to U restricted to gamma. The truss theory represents the truss theory. Let P be greater or equal to 1. Let's begin with the fundamental lemma. The lemma 9.9. Let omega be Rn plus. There exists a constant C such that we get the following inequality for all U in the set of C1 function with compact support on Rn. Now about the proof. Let G of T be equal to the absolute value to the power of P minus 1 times T, and let U be in the set of C1 function with compact support on Rn. We have then the following equality: G of Ux prime n minus G of Ux prime 0 equals the integral from 0 to n of the partial derivative of J with respect to xn in Ux prime xn dxn. Since U is a function with compact support, when n goes towards infinity, Gu x prime n goes towards 0, and G of 0 is 0 by definition of the function G, which means G of U x prime 0 equals minus the integral from 0 to infinity of the partial derivative with respect to xn of G. So G of x prime 0 is then equal to minus the following integral, because we use the derivative of a composition product formula. Now we take the absolute value of J Ux prime 0. It yields absolute value of Ux prime 0 to the power of P smaller or equal to the integral from 0 to infinity of the absolute value of G prime Ux prime xn times the absolute value of the partial derivative of U with respect to xn in x prime xn dxn. And we use some constant to obtain another inequality. So now we deduce the result of the lemma by integration for x prime in Rn minus 1. We deduce from the lemma 9.9 that the application giving the restriction on gamma of U, with gamma the boundary equals Rn minus 1 times 0, defined from the set of C1 function with compact support on Rn to Lp on gamma, can be extended by density in a linear and continuous operator from W1p omega to Lp gamma, since the set of C1 function with compact support is dense in W1p omega. This operator is by definition the truss of U in gamma, noted as U restricted on gamma, so we can give a meaning to the truss of U even when U doesn't belong to the set of continuous functions on omega bar. Then for the following, we can use two results depending whether U is in C omega bar or not. The theorem 9.17, where we suppose omega is C1 and U is in W1p omega intersect C omega bar with P greater or equal to 1. then the following properties are equivalent. If u equals 0 on gamma, it is the same thing as saying u is in W1P0 omega, and it goes in the other way around. In the proposition 9.18, this time we suppose omega of class C1, but u only in LP omega, with P strictly greater than 1. The following properties are equivalent. So we have two characterizations of the set W1P0. These last two results will be shown later, otherwise the lecture will be too long. So I'll talk about the proof in the other video. Now we focus our attention on the proof of theorem 9.27. We use for this the Stampaccia truncatures method. We fix a function g in C1 of R such that the derivative of g is bounded. All s in R, g is strictly not decreasing on 0 plus infinity, and g of s equals 0 for all s negative. We set k the maximum between the supremum of u and gamma and the supremum of f on omega, supposed strictly finite, and v equals g of u minus k. We make the distinction between two cases. The case where the measure length of omega is finite, then v is in H1 according to proposition 9.5, which says if g is C1 in here, g0 equals 0 and the derivative is bounded for all s in R, and u is in W1P of omega, then the composition between g and u is also in W1P omega. So we can say with P equals 2 that v equals g, composition of g with u will be in W12, so H1, because we know u is already in W12 of omega, so in H1. Here we apply this to the function g tilde, defined by g minus k minus g of minus k, so that g tilde of 0 equals 0, g tilde is C1, and the derivative of g tilde is also bounded. So like before, g tilde composed with u will be in W1P of omega, implying therefore g of u minus k equals v in W1P omega, because the term g minus k doesn't really bring any importance in what I just said. I'm going to explain why we use this added term. So v is in H1 omega. Why this choice for g tilde? If we directly chose g tilde equals g of g minus k, so v, then g tilde 0 would be equal to g minus k, and minus k can be strictly positive, so g tilde 0 would be different, wouldn't be equal to 0 in this case, and we couldn't go any further in the proof. So on the other hand, v is H1 0 of omega, since v is continuous on omega bar and v equals 0 on gamma, according to theorem 9.17. We recall that from the proposition 9.5, the gradient of g u minus k is eventually equal to g prime u minus k gradient of u. We then can inject v in 70, because v is H1 0 omega, so that we got the following equality. That is to say, with the formula of the derivative of g u minus k, we have the integral on omega of the absolute value squared of the gradient of u times g prime u minus k plus the integral on omega of u minus k g u minus k equals the integral on omega of f minus k g u minus k. But f minus k is negative and g u minus k is positive, and g prime positive since g is strictly increasing on 0 plus infinity. It's the same thing as saying it's not decreasing, and g of s equals 0 for all s negative. We deduce then that the integral on omega of u minus k g u minus k is negative. So we also know that the function tgt is positive for all t in R, so it means u minus k gu minus k is then equal to 0 almost everywhere. Then u minus k is negative almost everywhere, so u is smaller or equal to k almost everywhere. So u is smaller or equal to the maximum between the supremum of u and gamma and the supremum of f on omega, and for the other inequality, minimum between the infimum of u and gamma and the infimum of f on omega, smaller or equal to u, we do the same reasoning but with minus u. We just need to adjust the proof a little. In the case where the length of omega is infinite, is equal to infinity, then k is positive because f of x is smaller or equal to k almost everywhere on omega, and f is in L2. This implies that the L2 norm on omega of f will end up being smaller or equal to minus infinity if k is strictly negative. So we will have a contradiction because we know that the L2 norm of f on omega is finite. So we consider from now on that k is positive. Let us set k prime strictly greater than k. Then v equals gu minus k prime is in h1 omega. We apply proposition 9.5 to the function g tilde, giving g of t minus k prime. Then g tilde 0 equals 0, the derivative is bounded, and g tilde is in C1 on R. G tilde 0 equals g of minus k prime equals 0 because minus k prime is strictly negative. Moreover, v is continuous on gamma and v equals 0 on gamma. Since u minus k is negative on gamma, so v equals gu minus k is equal to 0 on gamma. So v is in h1 0 of omega like before. We are then allowed to put v in 70, giving us the equality 71. On the other hand, g of u minus k prime is in L1 of omega, since g of u minus k prime is greater or equal than 0 and smaller or equal to m times absolute value of u. Because gu minus k prime minus g of minus k prime is smaller or equal to m times the absolute value of u minus k prime minus k prime equals m absolute value of u, using the mean value theorem. And we know that g of minus k prime equals 0 because minus k prime is strictly negative. And on the set where the x on omega are such that g of x is greater or equal to k prime, we have k prime times the integral on the set of the absolute value of u simply is equal to the integral of the absolute value of u times k prime on this particular set, and we end up having that it is smaller or equal to the L2 norm of u on omega. L2 norm of u squared on omega, which is finite by a hypothesis. So the integral on the set where u is greater or equal to k prime of the absolute value of u is finite, and obviously on the set where the x on omega are such that u is smaller or equal to k prime, we then have u minus k prime is negative, so gu minus k prime equals 0. So for showing that the integral of the absolute value of gu minus k prime is finite, we only need to show that this following integral is finite, and that's what we just did, showing the integral of the absolute value of u on our set is finite. Then g of u minus k prime is in L1 of omega, and this little argument works because k prime is positive. If instead it's strictly positive, if instead we used k, we could have our integral with k equals 0, and we would not be able to use our little trick because the term on the left side will be equal to 0, and that doesn't give much information, because we already know that the L2 norm of u squared is always equal to greater or equal to 0. It's true, but that does not lead us anywhere, like I said. So we need q prime strictly greater than k. We then deduce from 71 that the integral on omega of u minus q prime gu minus q prime is smaller or equal to the integral on omega of f minus q prime gu minus q prime, smaller or equal to 0. And we also know that f minus q prime is negative and gu minus q prime positive. As before, the integral on omega of the absolute value of nabla u squared times g prime u minus q prime is positive. Here we also have a good use of q prime slightly positive, because k equals 0 will give the following inequality, and we cannot conclude. We wouldn't be able to go any further. So the integral on omega of u minus q prime gu minus q prime is smaller or equal to 0. It gives, as before, u smaller than q prime almost everywhere on omega. So u is smaller than k almost everywhere on omega, because q prime was fixed arbitrarily. We can take, for instance, k prime equal k plus epsilon. So if u is smaller than q prime equals k plus epsilon almost everywhere on omega, we then obtain, as epsilon goes towards 0, that u is smaller or equal to k almost everywhere on omega. And that's the end of the proof, because if we were to look at the other inequality needed for this result, we would just have to tweak something in the proof, like I said, changing u in minus u, or changing the k, for instance. So now we are able to speak about another theorem, the very important result in this video, the maximum principle related to the heat equation, which say that it is the theorem 10.3. It says that if we take the initial condition u0 in L2 of omega and let u be the solution of our three equation in the heat equation, then we have minus 0, the minimum between 0 and the infimum of u0 on omega is smaller or equal to u, which is smaller or equal to the maximum between 0 and the supremum of u0 on omega for all x and t in Q. Q is our cylinder, sigma is the boundary of our cylinder, and omega is the base of our cylinder. Q is equal to omega times 0 plus infinity, and sigma is equal to gamma times 0 plus infinity. Now we prove the theorem 10.3. We use here also the Stampaccia truncatures method. Let be k the maximum between 0 and supremum of u0 on omega supposed finite. We fixed the function g as in the proof of the theorem 9.27. We just saw that we set the following function h of s equals the integral from 0 to s of g sigma d sigma for all s in R. Finally, we introduce the function phi t equals the integral on omega of h u x t minus k dx. We show that phi possesses the following property. 17. Phi is continuous from 0 infinity to R. Phi 0 equals 0. Phi is positive on 0 infinity. Phi 0 equals the integral on omega of h u x 0 minus k, which is also h u 0 x minus k, equals the integral on omega of the integral from 0 to u0 x minus k g sigma d sigma dx, but u0 x is smaller or equal to k by definition of k, which implies that u0 x minus k is smaller or equal to 0, which also means that the integral from 0 to u0 x minus k g sigma d sigma equals minus the integral of u0 x minus k to 0, from u0 x minus k to 0 of g sigma d sigma. But for all t in u0 y minus k is 0, g of t equals 0, because g of s equals 0 for all s negative. And here it is not y it is x. So the integral from 0 to u0x minus k of g sigma d sigma equals 0, which implies phi 0 equals 0. Now, phi is positive on 0 infinity. Let's show that little result. Let t be greater or equal to 0, so phi of t equals the integral on h of h uxt minus k dx. Then h of uxt minus k equals the integral from 0 to uxt minus k g sigma d sigma. Now if uxt minus k is smaller than 0, then g sigma equals 0 on uxt minus k is 0. If uxt minus k is positive, then g sigma is positive on 0 uxt minus k. So h of uxt minus k is positive for all t positive, whether uxt minus k is positive or uxt minus k is negative. Remark, we work with t positive because we work on the heat equation. It would be logical to look at negative times when dealing with a diffusion problem. It would mean we were going into the past where we don't know anything because it has to start at time equal to 0. So phi of t equals the integral on omega of h uxt minus k dx is positive for all t positive. Then phi is in the set of continuous functions from 0 infinity to r. Let's have a look at phi. For all t positive, phi of t equals the integral on omega of the integral from 0 to uxt minus k g sigma d sigma dx. But g is in C1 of R, so it goes also for the integral from 0 to uxt minus k g sigma d sigma. It belongs in the set of continuous function on R. And same thing for phi of t, so phi is continuous from 0 infinity to R, we have shown 17. We also have phi is C1 from 0 infinity to R, with 0 excluded. That comes from phi prime t equals the integral on omega of g uxt minus k, which is C1 on R by hypothesis, and the times the derivative of u with respect the partial derivative of u with respect to time in uxt dx. This function is continuous on 0 infinity to L2 omega according to theorem 10.1, and h prime t equals g of t. So phi prime of t equals the integral on omega of the partial derivative with respect to time of h in uxt minus k dx, which is also equal to the following integral by derivation of a composition product. So then phi prime of t equals the integral on omega of g uxt minus k times the partial derivative of u with respect to time in xt dx, which is equal also to the integral on omega of g uxt Laplacian of u xt dx using the heat equation, the first equation in or three equation composing the system of the problema associated with the heat equation. Phi prime of t is then equal to minus the integral on omega of g prime uxt minus k times the absolute value of the gradient of u squared dx, and it is negative because here we integrate by parts, and g of uxt minus k is in h1 0 of omega for all t strictly positive. Why is g of uxt minus k in h1 0 of omega? As we saw in the proof of theorem 9.27, we use proposition 9.5. Since g is C1 of R, g0 equals 0, and the derivative is bounded for all s in R, and u is h1 omega, see theorem 10.1 from previous videos. So g of uxt minus k is h1 of omega. And we know also that u is continuous on omega bar times epsilon infinity, thanks to the theorem 10.1. So g of uxt minus k is also continuous on omega bar, and for all t positive, and u for all t positive, and u equals 0 on gamma according to equation 2 of the three equations associated to the heat equations. to the heat equation. So moreover, g of uxt minus k equals g minus k on gamma, and by definition k is greater or equal to 0 because k is the maximum between 0 and the supremum u0 on omega. Even if u0 is totally negative, then k will be positive or equal to 0, and if supremum of u0 is totally positive, k will also be greater or equal to 0. So g of minus k is equal to 0. Then g uxt minus k equals 0 on gamma and is in c omega bar for all t is totally greater than 0. You can then use, like before, this theorem 9.17 to obtain that g of uxt minus k is in h1 0 of omega for all t strictly greater than 0. It results from this that phi prime is negative or equal to 0 on 0 infinity, so phi is decreasing on phi 0 equals 0. It is decreasing and phi 0 equals 0, phi greater or equal to 0 on 0 infinity, and phi continues from 0 infinity to r. We deduce that phi is equal to 0 everywhere. So for each t strictly positive, phi of t equals the integral on omega of h uxt minus k dx equals 0. It means that h of uxt minus k equals 0 for all t strictly greater than 0. That is to say, the integral from 0 to uxt minus k of g sigma d sigma equals 0 for all t strictly greater than 0. But as we already saw it is the case only when uxt minus k is smaller or equal to 0. So finally, uxt is smaller or equal to k for all t strictly greater than 0, and x is in for x in q in the cylinder. Same thing for u greater or equal to the minimum of between the 0 and the infimum of u0 on omega, but we work with we tweak some parameters. It may not be necessarily changing u in minus u. So this is the end of the proof of the main result of this video. Last remark, in theorem 9.27 we suppose u in h1 omega intersect c omega bar, and we use theorem 9.17 to show u is in h1 0 omega. But with omega supposed to be c1, we can only suppose u in h1 omega, and we could use the proposition 9.18 to obtain u is in h1 0 of omega, because we know from the truss theory that we can give a meaning to the restriction of u on gamma. So that's the end of the video. I hope you found it informative, and I would recommend that you leave a comment below, like, and subscribe, but that's up to you. You decide. Good scrolling.